Welcome to Study Loop.
The question states that Huck Finn walks at a speed of 0.70 meters per second across his raft. That is, he walks perpendicular to the raft's motion relative to the shore. The raft is traveling down the Mississippi River at a speed of 1.50 meters per second relative to the river bank, figure 49. What is Huck's velocity, speed, and direction relative to the riverbank? I wrote down here what we were given in the question, and that is that the velocity of Huck Finn, which I write as v sub h, is equal to 0.70 meters per second. And since that has both magnitude and direction, I denote the direction as j hat. And the velocity of the raft is perpendicular to j hat, so I call that the I hat direction. And that velocity, which I write as v sub r, is 1.50 meters per second. I also draw a little graph here showing what we know, which is the direction of the velocity of Huckleberry Finn, as well as the direction of the velocity of the raft. And what we're trying to find is the velocity of Huck Finn relative to the riverbank. So the riverbank, I'm going to just write this as green. This is the riverbank over here. So we want the direction relative to the riverbank, okay, which I write as the red line VH prime for the prime version of Huckleberry Finn's velocity relative to the riverbank, and then theta, which is the direction. So magnitude and direction is what we're going to try to find. So VH prime here is, I'll write this out, is equal to the velocity of the raft, right, plus the velocity of Huckleberry Finn. Okay, well, that is equal to 1.50 I hat plus 0.70 j hat. Okay, and these are both meters per second, so I can put that on the outside. Well, since one is in the I hat direction and one is in the j hat direction, we cannot add those together, but we can find their magnitude, which is what we were asked to find. So the magnitude of VH prime which you can write the magnitude as these, the VH prime with these bars around it that represents magnitude, is equal to the square of, or I'm sorry, the square root of the sum of the square of both sides that make it up. So this would be VR squared plus VH squared. Okay, we can erase the square root here since we don't need all that. Okay, so if we plug in those values, we find that this is the square root of 1.50 squared plus 0.70 squared. Of course, this is in meters per second. If we plug these in, we find that this equals 1.66 meters per second. Locks that in, that's our magnitude. But we weren't just asked to find magnitude, we were also asked to find direction. So we can use the trigonometric identity. I'm going to write it next to the graph here, where the tangent of theta is equal to the opposite over the hypotenuse of that angle. So the opposite would be v sub h, and it's opposite over adjacent, I'm sorry, not opposite over hypotenuse. So v sub h, and the adjacent is v sub r. Okay, so we're going to use that relationship to find theta. So if you, now going back down here, if you solve for theta, theta is equal to the inverse tangent, which you could write as tangent to the minus 1, of VH over VR. And we'll just plug in the values for those. So that's going to be 0.70 divided by VR is 1.50. And the meters per second units cancel, so I'm not going to worry about that. So if you take the inverse tangent of that value, you find that this equals 25 degrees. Okay? And that 25 degrees, and we'll just write this out, is relative to the direction of the raft, or the direction of the bank, because the raft moves perpendicular or parallel to the bank. All right. Okay, and we can go ahead and box that in as our solution for the direction. So we have solved both magnitude and direction.